Okay, we start class and we go to here. 자, 혹시 어떻게 들을지 모르는 사람을 위해서 이렇게 들어옵니다. 그렇죠? Okay, we start. Okay, organic molecule should have carbon and hydrogen, but it's optional whether they can have either oxygen or nitrogen. It's optional. Sometimes oxygen, sometimes nitrogen. Even without them, they can be organic molecules. Okay, most of you chose light as the tool. We are going to study about the spectroscopy today. So this is the intro for that. Wow, surprisingly very distributed the answers. This was also multiple. No, the answer is hydrogen. Actually, the most abundant molecule in our body is water. Water has 1 oxygen, 2 hydrogen. So number-wise, the hydrogen is higher. Even though we remove water, dried material in our body, organic molecule, let's just say, still organic molecules, carbon number versus a hydrogen number, if you count them, maybe hydrogen number is a higher number than carbon, right? If I ask you the question by weight, then maybe carbon except the water. But if you count that the mole number, that means atom number or molecule number, then it should be hydrogen. So this is a wrong answer. Not N. Fortunately, nobody chose this one. So answer is H, proton. Maybe you have some of a physics student and materials science student and maybe other department student. To define the object of the chemistry, molecule is most likely it fits most of those cases. So we define the chemistry as a molecular science. 아니 어떻게 이렇게 잘 맞추지? 이상한데? In chemistry, we study molecule. Inside the molecule, we mainly study about the electrons, not the nucleus, not neutron, not protons. Let's check whether it is really true or not. 이번에는 뉴트론이라는 답이 있네. Chemical bond is formed by electron, not nucleus. Nature of a chemical bond is defined by electrons. Nucleus is very small and there's a lot of empty space. So the filling of material for that space is electrons. Again, the shape of the molecules, some of you answered the nucleus, but nucleus is just giving the position of those atoms, but the movement of the nucleus eventually driven by electrons. Electron drive the reaction, rearrange those position of those atoms, that means the nucleus, and eventually the shape is determined by electron, not nucleus. Yeah, when you learned about the Schrödinger equations, you are handling electrons shape and electrons position, and also electrons energy, not nucleus. Okay, so this is why we can say the chemistry is a topic of molecule, but among those molecule, it's a topic of electron, we can say. Okay, based on this, we start today's class. Okay, today we study about the conjugated compound and UV spectroscopy. Okay, we are in chapter 1 in today, the first chapter of this semester. And okay, you guys agreed that light is the most important tool to study molecule, right? And can you define the light? What is light? Hungjun, what is light?
Light is 무슨 전자 기파입니다.
전자기파이죠. You have learned that the light is a kind of form of an electromagnetic wave. So this is oscillating magnetic field and electric field make this kind of the wave. This is what we call the light. And this electromagnetic wave, depending on those the wavelengths, it can go to this direction and go to this direction. And then shorter wavelengths materials like gamma ray, X-ray, or UV, and small range of visible light, and then IR, radar, and the radio wave, like this way. So these all the waves all together, we call them electromagnetic wave or light. And energy-wise, the shorter, the stronger energy, and then the longer, the weaker energy that they have. So based on this, now we call this small range as visible light, and visible light has this kind of a color, right? The next question is, what is a color? Scientifically, or chemically, or physically, what is a color? How do you define color? Our eyes can see some small range of light, small range of electromagnetic wave, wavelengths-wise between 400 to 700 nanometer range. Those small range of electromagnetic wave we can detect using our eyes. And those light we call visible light. And among them, even we can distinguish different colors. What is color? 다들 너무 샤이한 거 아니야? 다연, what is color?
I think color is wavelength.
Color is the ability to discriminate different wavelengths. Wavelength is the keyword here. Okay, so here, this is range of visible light, and then this is a 400 nanometer up to a little above the 700 nanometer range. They have a different wavelengths, and this wavelengths can be detected by our receptor, color receptor. Our eye has 3 different color receptors, RGB, 3 different receptors, which has a different sensitivity to different wavelengths. And this is the coding, the assemble these different wavelengths, and then they can be sensed by small numbers of cone cells in our eye. And then there is a process in the brain. And eventually, this is just a wave, which has a shorter wavelengths and longer wavelengths. And our brain rearrange those information and then deceive us, make illusion or perception. That end result is what we sense as a red color, green color, blue color, kind of colors. Color is just a perception. The physical property of this color is a different wavelengths of the light. Okay, so now here we put this kind of a different range of the colors from violet to red color, or like this. This kind of the color range or the color spectrum we have seen somewhere. Where did you see this? What is the most common source of this color spectrum? In nature, where can you see this kind of a color spectrum?
빛인 것 같습니다.
Sorry, Sangbin?
Rainbow.
Yeah, it is rainbow. This is a very the easy source we can see, even though we did not know about the colors. At least we could see this kind of a phenomena from nature time to time after the rain, right? Rainbow has from violet to red color. How many colors are here? Well, we count maybe 7 colors, but that's arbitrary we chose, right? In English word or the different language word, they may have different numbers of a color for rainbow. And actually there are maybe thousands of different wavelengths included here. This is a continuous range of different wavelengths of light here. So the definition of a spectrum means it's big bundle from here to here, and it has different range of different wavelengths of light, the wave. This is all together as a bundle, continuous bundle of something. This is what we call spectrum. So originally, the word spectrum is made by this rainbow kind of a continuous light, and then later it is used in different fields, like a political spectrum or a different kind of a social science spectrum. It's changed into different word, but original term here are made by this continuous light bundle is the spectrum, right? So one way of we can see this light is in nature is rainbow, but this kind of the separated light into different wavelengths, even artificially we can make using prism. And here this prism, if you think about the input of this prism, is actually this is a white light. White light, you may think this is a pure, without any noise or any special thing, but actually it's the opposite. White light is a mixture of all light together, then it forms white light. So white light is not pure. It is complex of all different colors, then make white light, right? And we have this range of visible light, and outside of this red light, there is still continuously, there is some longer wavelengths of light there. What do you call them? Longer wavelengths of light than visible light. What is it?
Infrared.
Infrared. They said infrared here, outside of the red light. How about the outside of violet?
Ultraviolet.
Ultraviolet. Now the term looks like a ultra means it's a higher, right? Infra means it's a lower. Then maybe we should not draw this the spectrum like this. Maybe it's the opposite way, like this. So UV is energetically it's a higher, and then IR is infra, energetically lower. This may be right direction we could use. And today we are going to study about the UV spectrum and UV spectroscopy. And UV, depending on those wavelengths, even we can divide further. Shorter, the longer one is A, and shorter one to this way. This is A, B, C. C is shorter than B. B is shorter than A, kind of things. Now, today we are going to study about this interaction of light and matters. Then let me ask you, what kind of interaction can happen between light and molecules? In Korean and in English, you try to say. Jogunim, you count.
Vibration.
Who is giving the good answer? I heard something vibration. Okay, what is vibration? Is the Hyunsuk said, Wonsuk said vibration. Vibration is the result of light and molecule. Yes, it's kind of. What kind of light can generate vibration?
Microwave.
Microwave maybe, or other source? Microwave may be a little too long or too weak.
Higher can make vibration.
Say again.
Higher infrared can make
Yeah.
vibration.
This is good. Infrared is usually in, the generate the vibrational mode of the molecule. Infrared is the range of molecular vibration inducing part. But my question was, what is the interaction? This is a source of light which can generate the vibration. This vibration is also made by absorption. Okay, absorption is a 흡수, right? Absorption is a one interaction. If the molecule absorb IR, infrared, then it generates a vibration. That's true. But interaction phenomena is absorption. So absorption is a one. What is?
Emission.
Emission. Okay. After observed, then those observed light can emit. Emission is another way. Other?
Fluorescence.
Fluorescence is a kind of emission, we can say. Other?
Scattering.
Scattering, good. Scattering is another interaction between light and material or the molecule. Anything else?
Dissociation.
Association, you said?
Dissociation.
Dissociation. Dissociation is something happens in the molecule. from the molecular the view of aspect, the molecule can be divided into two. That's a dissociation. So this can be a little different aspect. Others,
Scattering.
we had a scattering here. So far we had absorption, emission, scattering. Anything else?
Energy transfer.
Energy
Transfer.
Energy transfer. Energy transfer can be done by observed and then observed by another material. That can be energy transfer, we can say. Then it is a combination of absorption. Let's try to think about the single step of the event or interactions. Okay, some others may be reflection, 반사, and refraction, 굴절, kind of different things. Now, reflection and scattering, they looks like different, but eventually they are same event. This is just a smooth surface, it make reflection. If it's a rough surface, it generate the scattering. So there are many different kind of interactions you can say, but altogether, if we divide them, we can classify three aspects: absorption and scattering, and then re-emit, emission. These three, we can define all different kinds of interactions of matters, of molecules, and light together. For example, let's just say metal surface. On the metal surface, the common aspect or common property of a metal surface is a shiny surface, right? Then this shiny surface, similar to mirror. This shiny surface is one of those the phenotype phenomena by interaction of light and material. Then among this, what event happens on the surface of the metal or on the mirror? I already gave you different examples here. You can choose one of them.
Reflection.
It should be reflection, right? Coming in and then scattered into same direction. That's reflection. Now, next question is, what material, which part of the material interacted with the light in this reflection phenomena? It is a matter or molecule or material, but which part of the molecule interacted with the light?
Free electron.
That's an electron. That's a free electron. 자유전자, recall, there's a lot of free electrons on the surface of a metal, and then they make this a smooth surface, and then they scattered into the same direction. That ended up as a reflection. Okay, so this is another evidence that when we say about the interaction of light with the material, and those interactions are not interacting with the nucleus. All of those interactions we observe, they are interaction between electron and light. Scattering is that electron is irregular, then it generates a scattering. If it is even like a free electrons, then it generates reflection. Okay. The next question is, what would be the term of this study, interaction of light and molecule? You know the term.
Spectroscopy.
This is a spectroscopy. Who gave that answer?
저요 교수님. 네,
이현아가 답,
이현아요.
현아가 답했네. Yep. Spectroscopy is now we can define spectro means that this is spectro came from spectrum, right? It's a bundle of the light, means different wavelengths of light, and then scopy means it's observing, seeing. With the light we see, that's a spectroscopy. If you don't use light, then you don't call this spectroscopy. Always you use a light, and by using that interaction between light and molecule, then there is a spectroscopy. Now today's topic is we use UV. Then if you use UV and study, what do you call? Obvious, right? That should be UV spectroscopy. Similar way, in the organic chemistry 1, you guys have learned IR spectroscopy. This is a different range of interaction we study. IR case, already we heard some the suggestion that IR may be the one of those interaction. It generates vibrational the motion in the molecule, and we can get the information about the vibration of the molecule using IR spectroscopy, right? Today we are going to study about the UV spectroscopy, different aspect of those interactions. And you guys also have learned about this NMR, right? NMR was spectroscopy? Yes or no? Yuzong, NMR was a spectroscopy?
No.
No, it is not. She said no. Then what is it? NMR? Yuzong said no for NMR for spectroscopy. What is the reason? Because we didn't use a light here?
Yes.
That is a good analogy, but actually NMR is a spectroscopy too, because here we used microwave. Microwave was used for NMR. That's why NMR is also we call NMR spectroscopy. How about the mass? You have learned mass 2, mass spectroscopy. Does it make sense? If you look at those chapter name of mass, mass has spectrometry. Scopy means we see, vision. Metry means measuring. Interestingly, in mass spectrometry, there is no component of light involved there. They use magnetic field and separating those the ion by their weight, but there is no light. That's why mass spectroscopy is a wrong term. Okay. Spectroscopy, you need to have any kind of light there. That's a spectroscopy. Makes sense, right? Okay. I guess you guys are not in the Hanja generation, but anyway, at least I hope you can read this. Somebody can help? Yoongyong, could you read this? Yoongyong, Yoongyong?
Sorry, Professor, I can read that word.
You cannot read? Okay. Hyunbin,
Yes, Professor.
can you read?
Oh, I can read 중.
You can read only 중? Okay, who can read them all? 이것도 점수 줘야겠네. 케미스트 클래스에서 한자 읽었다고 점수 주는 게 좀 웃긴가? 그래도 수업을 도왔으니 누가 읽어볼래? 이거 읽은 사람이 하나도 없어?
근동인 것 같습니다.
오케이. 더욱이 앞에 거 근동, 두 번째 거는
죄송하나요? 중동인 것 같습니다.
중동, 다음은
원동인 것 같습니다.
원동, 그 다음은
극동?
극동, 좋으네. 자, 말로 들으니까 들은 적이 있는 것 같죠, 그죠? In English, we say this is Near East, Middle East, or Far East, or 극동 maybe far, far East. So this word is used like this. So this is a 근동, Near East, Middle East, Far East. This is a far, far East. 이렇게 보면 누구 관점으로 본 건가요? 가깝고 중간이고 멀대요. 누구 관점으로 봤을까?
유럽인 것 같습니다.
이 사람들 관점으로 본 거겠죠. 어느 관점으로 봤냐에 따라서 지네 마음대로 우리는 극동에 있다고 얘기를 해. 그죠? 관점이 중요합니다. Same way, if you look at here, now we have a visible light here. Then this is infrared and this is UV range. Then we can say maybe here, if the UV is here and here, if you compare them, we can say this is a near UV. This is a far UV or deep UV. If it's a deep UV, maybe this is a shallow UV, right? So the origin or standard point is here. We can look at the visible light from our view point. That's why we define, okay, near UV, near the far the UV. Same way, right next to red light, we call near IR. Then the longer one we may call far IR, right? Exact the wavelengths is not so important, but at least we can recognize. It would be good to recognize if it's near to the visible light, we call near UV, near IR. Makes sense, right? And here, at least I wish you know those boundary here. Shorter wavelengths of the visible light starting from the 400 nanometer. Longer one, depending on your age, I can see maybe up to 680. You guys can see maybe 750. Young babies, maybe they can see 780. Okay, depending on your age, the ability of seeing those wavelengths is becoming shorter and shorter. So 400 to 700, that's visible range. Okay. Now, if you say this is colorful material, chemically speaking, we already said that this color material is the container of a specific wavelength of light. That's what we need to make a colorful material, right? Then the next question is, how can you generate those light capturing materials? In this case, we didn't say much yet. These colors are all by absorption. IR spectroscopy is absorption spectroscopy. UV spectroscopy, that's also absorption. IR can generate vibrational mode that is done by absorption of IR light. By UV absorption, there's something else also can happen. But anyway, this color perception can be generated by observing those some range of visible light. We said UV spectroscopy, but why am I talking about the visible light? Actually, UV and visible is usually we use it together. UV visible spectroscopy is more common other approach. That's why we handle them together. Okay. Now, by looking at these colorful materials, let's think, how can you make light absorbing material, especially specific wavelengths absorbing material? How can you do that? Any idea? Or anything you heard? Or any property of a colorful material?
Conjugation.
Conjugation is the one thing. That's what we are going to learn today. Other than conjugation, any other example? Do you know?
Some inorganic chemical. 그 결정장 이론.
Crystal field theory, 결정장 이론에서는 usually it's not organic material. They are more inorganic material. Those inorganic material, inorganic means non-carbon, non-hydrogen, and other materials, especially some kind of metals, especially heavy metals, which has a d orbital. So you guys have learned about the s orbital, p orbital, and complicated d orbital. Now, those gap is smaller and smaller. Those d orbitals has very small gaps, and they have a chance to absorb the light. So Sang-Bae's point is, if the molecule has a heavy atom or heavy metal, they have a chance to absorb the light. Like copper 2+ is a blue color. And different kind of metals has different the color materials. If you don't have the metal, now the only way is we use the conjugation. So before we go to the conjugation, let's just think about the chemical bond. In the quiz, we said that the chemical bond is defined by electrons. Let's check whether that's true or not. Now we have here one bond. We call this the CC bond as a sigma bond, right? And when we draw one line here, there are electrons forming up here, make connections together. And these electrons are surrounding these atoms and bind them together. This is what we call chemical bond. When we draw one line, how many electrons are here?
So,
Always this one bond of electron, we put 2 electrons. Single electron is not stable, and they are called as radical. and radicals are not so stable, and they don't exist for a long time. When they meet together with a different spin, that we talk later, and two electrons can have a chance to make a one bond, chemical bond. And this kind of a bond is relatively stable. And last time we learned about carbon-carbon bond dissociation energy, right? Approximately, how much was the bond dissociation energy between carbon-carbon? Nobody remember? It's good to
80?
remember. About 80 kilocalorie per mole. Range of light, range of energy is required here to break this bond. Okay. When you say break, there are two ways of breaking. There is a single bond here. Electron is moving like this. If you draw arrow like this means two electrons are moving. Okay. When you say bond breaking, that breaking happens, one electron moves this way, the other electron moves this way. This is a bond breaking, homolytic cleavage. The bond dissociation energy is the energy required to break this bond homolytically, equally, symmetrically. So you have seen here, this half a head. This means this is a single electron is moving. Okay. If you see this is a two electron is moving. Now, this sigma bond is quite stable. That's why to break this, we need quite high energy. In terms of light energy, that's belonging to UV light energy. So that's why strong UV, if you go out to the sunlight, it may be harmful to your skin because those sunlight, the UV light, can break the chemical bond in your biological materials. Okay. Now, this is one kind of a bond. Today we learn, actually, you know those bond, double bond. Now, this double bond or the triple bond we use, these bonds looks like a two sigma bond, but actually it's not. We already know that, right? First bond here is one sigma bond inside here, similar to alkane. But second electron pair is not localized mainly inside here. They are localized outside here. Partially, they are helping this bonding. But this electron is much loose and much freer than sigma bond. They can move around freely, relatively, inside here. This kind of a bond we call pi bond and or pi electron. Okay. Using this pi electron, we can make light absorbing materials. That model you guys have learned in general chemistry, particle in a box model. Now, before you learn the Schrödinger equation is the describing the motion of electrons. Before that, you learned this simpler model, something like this. In the defined box, with an infinite range of potential energy well, and inside here, let's say there is a particle is moving around. And this particle movement, let's describe that as wave. That is particle in a box model, right? Now we can use this pi electron and sigma electron similar to this kind of model. Now in this case, this box is defined by sigma bond. Because it's relatively stable, it's not moving that fast, but phi electron is moving relatively fast here. Then we assume that this particle inside here, this particle is a phi electron. Actually, that model works quite well, and we can utilize that particle in a box model. Particle in a box model is just a simple mathematical model. It does not apply to atomic the orbital description. Atomic model, we have nucleus at the center. And then we assume that there is moving around the electrons around here. This is a model of a Schrödinger equation, right? Using spherical coordinate. And we just use nucleus position, just fixed. Relatively, this is a slow motion. That's why we just fix nucleus is not moving, we assume. and only count those movement of an electron. That's why the object of Schrödinger equation is electron, not nucleus. Now, similar simpler model here, this can be used for 5 electrons. And this one, then how can you make a different size of a box? Now, this box, if this is a single alkane, this is a small box like this. We can connect this box. There's another box here, and we connect those boxes. Then this box becomes almost a double size or even bigger than double size like this. Now we can assume that this whole size of box size is defined by sigma bond, and the electron is moving around like this. Here is a very small box. So to jump this into the next level like this, they need to observe quite big energy. Now, if the box size is the bigger, then to jump this energy to the next level, relatively small energy, they can jump up. So this is the model of this event we call conjugation, connecting of a double bond. That's conjugations. And the result is, practically we are increasing the size of a box, of a particle in a box model. Okay. If you look at the bond length, carbon-carbon bond is approximately 1.5 angstrom. 1.5 angstrom is a 0.15 nanometer. We don't want to call 0.15, so if you change it into picometer, nanometer is 10 to the minus 9, right? How about the picometer? Picometer is a 10 to the minus 12. Okay, this is commonly used, so it's better, it would be good to at least know this unit. Angstrom is a 10 to the minus 10, right? Carbon-carbon bond length is 1.5 angstrom. Double bond is a slightly shorter, 1.3. Not half, but slightly shorter. That's why it's stronger. Triple bond is even shorter, 1.2 angstrom. If you look at the alkane, this carbon-carbon bond is similar to CC bond. In alkene, this double bond is similar to double bond size like this. In the middle here, looks like this is a single bond, but that character, actually, it's not fully single bond length. This is a little shorter than that. That means this is single bond in conjugation system. This has a partial double bond character. That's why we can say this electron can move from here to here like this. Okay, that is the effect of a conjugation. Now, this pi bond can be described this way. If it is only one pi bond pair, then it can fill up 2 electrons in here. And then this is the next level. 2 atomic orbital combined together to make this a molecular orbital. And then this is the filled one. And this is the unfilled. Filled one we call, anybody knows the energy level of this range? I guess you may learn from general chemistry. Energy level over here and here, there's some name you call. You don't remember? This is called as a HOMO. Highest occupied molecular orbital. Then anybody remember the opposite term here?
LUMO.
LUMO, Hyuna said LUMO, good. LUMO is lowest unoccupied molecular orbital. Here there is an energy gap. This is one size of a box. So in the particle in the box model, we learned it can generate this, the form of a wave. Next energy level, there is forming this kind of one, right? There is many different energy levels here. To jump from here to here, you need to observe the light. You need to introduce the energy. That energy is matching to UV visible light energy. So by generating this kind of conjugations, make this box bigger. Now those are jumping. So here you can draw the line here. This is a HOMO and this is LUMO, because in this case there are 2 pi bond pair, you have two sets of electrons. So two electron here, two electron here. Now this electron can move up here. Because of the bigger size of a particle, the particle in a box, they need just a smaller the energy, the longer wavelength of light. Okay? Now, if you compare these two things, here, this one in one, the double bond, another double bond is connected this way. This is a conjugated system. In comparison, this one, there's a separating carbon in the middle. This double bond is not conjugated. If you look at the molecular orbital, this one has red color is pi electron at the density. Now here one, here one. This is a two isolated system. When they are conjugated, the middle side is connected, and you can see a partial red color here, right? That means this single bond, nominally single bond, but this one actually has a partial double bond characters. Big difference here, pi electron, they can move only here and only here. That's why to jump this into the next level, they need very high energy, short wavelengths. If it becomes conjugated like this, now the pi electron can move from here to here, quite a big wave, bigger wave. That's why they require the lower energy. Now we can compare, if it's a single double bond, what kind of energy they need to jump? 171 nanometer. It's much shorter than visible light range, 400 nanometer, even shorter than maybe UVC. 170 nanometer is a very strong light. So to break double bond of ethene, you need a very high energy. Very difficult to excite. Now 217, longer wavelengths you can observe, right? 3, 258. Now, can you see some trend? Approximately one double bond generate how much are the extended wavelengths to observe? 4, 290. Still, it doesn't have a color. It doesn't have a color means it's not in the range of visible light, right? We cannot see them. They still look like this white powder. It doesn't observe any visible light yet. Now, 5. Now, can you guess what is the other wavelengths here? By looking at those trend, approximately how much is added? 30, 40 nanometer is adding, right? Then you can assume approximately maybe 330, you can say. Now start to see a little color. Still, that's less than 400. Still, you can see that because this wavelength is peak wavelength. This is 335. Maybe around here, maybe start to invade 400. That's why you can start to see a little color. Now, longer than that, definitely you can see the color. 360, approximately 30 nanometer. 7, oops, maybe nobody has made it yet. It's not reported. 8, now you can see strong colors, orange color. And going further, no report. 10, no report. 11, 470. Now it's in the range of red color. 12, 15, something like this. The color order it's not rainbow color order because this is not emitting light. The color we sense is the wavelength of the light reached to our eyes, right? So this is observing. That's why we have a full spectrum of light. Then if they start to observe this range, then we see those complementary colors, 보색. They started to observe maybe violet light. Complementary color of violet is yellow. That's why we started to see yellow colors. Okay. Now, using this, can you memorize some of these numbers? If I show you this, then can you guess what this molecule is? You already have a notebook, right? You can see them. What molecule is this? How many conjugation there?
2.
2, right? So here we see here 217. I said UV visible, the UV visible spectroscopy is an absorption spectroscopy, and then this is lambda max. This is the typical shape of UV visible spectroscopy, observed at this wavelength, and then this one tells you that this molecule has some motif like this. Okay, if there's a molecule, shape is like this. I make it more complicated molecule like this. The UV spectrum between this molecule and this molecule may not be very different. They may be very similar because even though they have a quite a big molecule like this, all of them are conjugated, they're connected by sigma bond. Sigma bond does not count for those small box size for the pi electron. Pi electron only can move here, right? That box size is the same as this size. So using this information, now we know that UV spectroscopy can tell you what kind of a conjugation system, how big is the conjugation system. That information you can get from UV spectroscopy. And in UV, usually it's quite smooth single bond, single peak, you can see, or maybe two peaks like this. So using this information, if you look at those tables, now here again, two conjugation connected together, similar, 217, 220, a little difference with a small substituents like this. If there's some trend like this, then you can see those effect of by adding one alkyl group, how much changes we can expect, kind of things. Now, if you look at this one also has a two electron, two other pi bond, but wavelength is quite different. This may be because of this ring structure effect. And here, this is a 3 pi bond. This is the number we have seen. 4 we have seen. And then this one. Now, so far we have seen only carbon-carbon, the double bond. Now here, carbon-oxygen double bond. But if you look at those numbers, this number, very similar to each other, right? So the heteroatom effect here, rather than the oxygen, not the carbon, the effect is not so strong. Means this double bond character is more important. Size of this pi system is more important, you can assume, right? So this is the conjugation system and matching the observing the wavelengths here. Benzene, 3 other pi bond, but this one is quite different from this. So benzene has a very unique property, much stable than other molecule, and its own unique property, which what we call aromaticity, aromatic property. That is what we are going to study next week. Okay? So other than benzene, other than cyclic form or other linear forms, we can have general trend, and we can estimate those size or the wavelengths of those light. Okay. Now here, this molecule is a keratin, beta carotene, which is the main colorful material in carrot. Can you count how many pi bond here? Okay, 11. What's that, Junyoung? Junyoung said 11. If it's 11, then what is your answer for the wavelengths? We have a table. As you can see, the uploaded the lecture note, then you can see those table. What do you expect?
470.
470, and this the beta carotene wavelength is 455. Maybe small changes of induced by this IQ change, or maybe this the ring change that affect a little, but main peak is similar enough, 470, 455. So that means if you can guess by calculation, by looking at those molecules, if you can get the idea, okay, this may be around the 450, 460 range. That's good enough. Then you can guess the color of these molecules. Okay. Now, if you look at the spectrum of this, it has peak as a 455. Now, this is not very smooth, right? This has some small peaks here and there. That implies that this molecule is not the particle in a box model. We assume that this box is a flat size, and then the electron is moving freely from here to here like this. But actually, maybe it's possible that there is some bond is rotating, and then it acts as a conjugation system as maybe like this. That's also possible, right? And then some of them, if it's a smaller and smaller, then they may observe shorter wavelengths, and then maybe shorter peaks here. These guys may reflect those small size of a box characters. Okay, maybe bigger one. There's a bigger one there too. Maybe the biggest one is utilizing the whole size. Maybe that is not very stable. Maybe this one is the most abundant box. That's why this is a little smaller than 470. And there is even bigger box, but it's not very popular. Most stable box is this one. That's also possible. The study you can make. Now, if you look at this kind of the conjugation system, and then if I ask you, hey, can you make colorful material, beautiful colorful material, which can stain our clothes? Maybe before the organic chemistry has developed the synthetic dyes, we extracted out this kind of a colorful material from flower and maybe from carrot or different kind of natural materials, right? But problem of these materials are, they are not so stable. So we use time to time detergent, bleach molecules. Bleach molecules can work by oxidation or reduction. And oxidation can happen by oxidizing this one like this. Anyway, breaking up this phi bond. Reduction can happen by hydrogenation, adding here and here. Anyway, remove any of those phi bond in the middle. That means any of those bleaching molecule, oxidative, reductive, they can break up this bond any place here. That means this dye is chemically very unstable. They can be decomposed very quickly. Then it's not good dyeing material, right? That's why the organic chemist, they tried to make this box colorful material, but one way is to make the box size bigger. But as I said, if you make a bigger box size, then it's chemically unstable. That's why another trick is to make this box effectively bigger by applying this electron donating group. Then the energy status is going up. Size-wise, this is not this way, not too big, but it goes this way. Effective box size is becoming bigger. Electron donating helps. Then how about electron absorbing, electron poor? Then it can go one way, go to this way, one way, go this way. Effective size of a particle in a box, the box is becoming bigger and bigger. Utilizing these molecules, this concept, most of those colorful material we see in the clothes on any kind of the staining material, they have electron donating group and the electron withdrawing group and some kind of conjugation system, sometimes protected by this ring structure. And those conjugation number 1, 2, 3, 4 is not too big, but still these molecules are quite strongly light absorbing molecules. One example is, let's say, crystal violet. Spectrum is like this. Spectrum, if you look at about 590 absorption. And this color, this is observed. So we cannot see this color. We can see leftover red color and blue color. Red plus blue is a violet, right? That's what we see as recognizing colors. So this is common structure of colorful materials, utilizing this particle in a box, but a little more synthetically generated particle in a box. Okay. Now, utilizing these materials, let's say bacterial staining, gram positive, gram negative. This is the crystal violet materials. Out of this white light, the background, and if we can observe one kind of colors, in the case green color, then we can see this kind of strong the violet colors. So this is the conjugation and also the UV spectroscopy of the phenomena. Now let's study a little about the chemistry using this the double bond. I told you already last time, if you study those organic chemistry 1, this would be quite helpful to study about the reaction of alkanes. 5 electrons is a little free electron. That means it is electron-rich species, it has chance to donate that electrons, like a nucleophile. Here, if you have this kind of reagent, one positive, one negative, the pictures here, then these electrons can move like this. I draw arrow like this, that means the 2 electrons are moving, right? If this electron is moved that way, they can capture 1 proton, and then proton can be captured here or here. And you learned from organic chemistry 1, depending on those position of, if proton is attached here, then positive charge is introduced here, right? Then you learned about the relative stability of a carbocation, this cation versus this cation, primary cation versus a tertiary cation. Which is more stable? Tertiary cation is more stable, right? That's why this is dominant intermediate. Then this position can react with the leftover Cl-, then it can form this kind of adduct. Now, and the result is proton is added here, right? And chloride is added here. You follow that, right? So this kind of reaction is addition can help can happen to alkane with this HX molecules. Now, how about this? Very similar. Now, this is a little conjugated system, right? Then again, first movement is this extra electron attack electron poor positions. Then it can generate cation. Oops. Cation like this. Double bond is still here, right? Maybe competing species may be this one, but we already have seen that among these, this is not so stable. This is more stable, right? Then next step is maybe the Br can be added here, so it can form this product. That's one way. But if you do this reaction, actually, there's 2 kinds of a product happens. This is what we expected, added here. But sometimes Br is added here. That's because the intermediate, this intermediate can be rearranged. This is allylic position next to double bond, and then this electron can donate this way. Again, I put 2 electrons, and the result is this way. And here, if the Br is attached here, then it can form this product. So 2 ways are possible. Now, if you look at the condition carefully, if you look at, in this case, it is added 1-2 position, so it is a 1-2 adduct. In this product, the addition was happened here and here, 1, 2, 3, 4. This is a 1-4 addition, we call it. If it is a low temperature, this is a preferred. If it's a high temperature, this is a preferred. It's the same reaction, but depending on the conditions, the product is different, right? So if you look at those the event, then starting material was the same, but sometimes it goes to B, sometimes it goes to C. And if you draw those reaction profile, you can draw this way. This is going to the B pathway. This is going to C pathway. If you look at the stability of the product is determined here. Then this goes how much become more stable is determined by this factor. Another factor we can see is how fast is the reaction. Speed of reaction or kinetics, it is defined by this size of activation energy. Activation energy is smaller, then reaction can go easier. That means reaction is faster. That means A pathway, B pathways. B is less stable than C, but if you reduce the temperature, low temperature, it goes into the kinetic control. Means those intermediates formed before it is rearranged to different forms, it goes to the B pathway first. So kinetic control, you need to decrease temperature. Makes sense, right? If you increase the temperature, even they can go B and can come back, and go to C, full equilibrium. Then end result is most stable compound is accumulated at the end. That is the case of one product. So two control is possible. One control we call kinetic control. The other control is stability-based thermodynamic control. Kinetic control, you want to use a low temperature. Thermodynamic control, you want to induce the full equilibrium and then generate the exchange of those all components. That's a thermodynamic control. Make sense? Okay. Just one more reaction. Now we just learned about this conjugated system. 2 pi electron connected together and 1 pi electron. And interestingly, when you connect the mix this together and heat it, and it forms very interesting product like this. Seems like pi electrons that they rearranged. Sigma electron is not changing. Pi electrons is moved like this. Direction is the opposite way is also possible. By making symmetric transition state, and then it forms this kind of a product. And very efficiently too. And this reaction can be induced by thermally or photochemically, both ways are possible. This reaction is named as a Diels-Alder. And the name of this reagent, if you look at here, this one is a diene, 2N. And this one, like diene, so that's why this is called as a dienophile. This is similar to nucleophile, electrophile, right? Electrophile means electron poor. That's why they like electron. Nucleophile is electron rich. That's why they prefer to bind to electron poor nucleus site. That's a nucleophile. This is a diene, and this is a dienophile. So this reaction is so efficient, and then this reaction becomes very popular. And Diels-Alder is the chemist name of the inventors of this. This person is a Diels. This person is an Alder. They got Nobel Prize by discovering of these famous reactions. So by looking at a little more examples like this, now here we have a diene, and this one is kind of a diene, but in this case, they played as a dienophile, interacted together, and then make this product. Okay. Now if you look at the stereochemistry, looks like this one goes into the same direction, right? And now, if you look at this one is the same material like this, but this is cis form, this is a trans form. Can you guess the product, the stereochemistry? It goes into the same one. Now this generated cis product, and then this is generated trans product. Means here is the diene, here is the dienophile. They approach same directions. They do not change. Okay. So this reaction happens only in thermodynamically. If you induce this reaction by light, then this stereochemistry is changing. But this is above the level of the organic chemistry too. We are going to handle only thermodynamic, the thermal reaction, not photoreactions. So you can just think in your level, this Diels-Alder reaction happens in the same direction. Okay. Do you think this reaction can happen? Previously, it was this shape of a diene. Then it can form the reaction with this motif. But now this is not that shape. But it is possible by looking, this bond is partial double bond character, but it's a stronger single bond character. They can rotate. Means by rotating, it can generate conformation like this way, and it can react. Okay, so this changes. The previous one was like this. This one is a trans form, this is cis form. But usually the trans cis we call is across this double bond, right? This is through single bond. So this is not real cis or the real trans. Cis trans change is requires very high energy. But this one is relatively easy to rotate. And that's why this is not fully cis, fully trans. So this is called as a S trans, single bond trans. SCs. Means with a reasonable energy they're providing, they can rotate. Okay, and then it can form this kind of a DSR product. So we're using this diene and dienophile make this product. And stereochemistry is from the same directions. Okay, so this is a small reaction part of the today's lecture. And today we have studied about UV visible spectroscopy and the origin of it. That is conjugation and also conjugation size. We can obtain the information there. And then a little reaction, DSR reaction and thermodynamic and kinetic control we learned. Okay, next class is the next Tuesday. You guys have a Chuseok, so Merry Chuseok. And after that, still we will have one more week of the online class. I will put assignment 2, but this assignment 2 is for next week. Okay, so assignment 1 was for this week, and then this is for next week. And today I got the 24 other assignment from you guys. Couple of you didn't send me yet, so you may send me your assignment 1 if you didn't yet by email. Okay, and I put those deadline is a little more extended just before the class start. Okay, but finish up those by the time, then you are ready to study the next the chapter. If you do yes up, that is great, but at least let's do box up. Okay, so by this time you solve those problems. I will put 5 problems, and that's a mandatory part. If you solve more problem, then you send me separately by email. Okay, then I count that as an extra point for that. Okay, now we learned we finished the chapter 14. So next week is chapter 15. Benzene and also aromatic compounds property we study. Okay. Any question for today's lecture?
질문 있습니다.
Go ahead.
아까 그 베타카로틴의 흡수 스펙트럼에서
Go ahead.
그 스펙트럼의 피크가 여러 개로 나오는 것을 확인했었는데, 물론 제일 높은 피크는 있지만 그 옆에 작은 피크들이 있는 걸 확인했었는데, 이 베타카로틴이 그 이유가 일단 결합이 회전해서 그런 걸 수도 있고, 왜냐면 결합이 회전되면 이제 P 오비탈끼리 잘 겹쳐지지 않아서 그런 것일 수도 있고, 그리고 고리 구조가 있기 때문일 수도 있기 때문이라고 말씀해 주셨는데, 그렇다면 두 페이지 전에 있는 이거보다 2 슬라이드 전에 있는 그래프에서 그 전이요. 네, 거기서 너무 그래프가 깔끔하게 나오는데, 이건 아까 파이결합 2개가 있는 컨주게이트 시스템이었잖아요. 근데 파이결합이 2개라면 시그마 결합의 특성은 더 강해지기 때문에 더 잘 회전할 것이라고 생각이 드는데, 피크가 하나만
우리가
나오는지.
파티클 박스에서 박스를 만들 수 있는 가능성이 이 가능성과 이 가능성 2가지가 있겠네. 그런가요? 여기서
네.
파일렉트론들이 얼라인을 할 때 파일렉트론이 예를 들어서 파일렉트론 하나가 있고 하나가 있을 때 파일렉트론들이 동시에 이렇게 써 있으면 이것들은 박스 위에서 같이 움직인다고 생각할 수 있는데, 이게 이렇게 되어 있으면 이거는 컨주게이션이 깨진 상태인 거죠.
그러면 그냥 오른쪽, 네.
기본적인 가정이 모든 파일렉트론들이 같은 평면 위에 있을 때만 컨주게이션의 효과를 가지겠죠.
네.
그렇기 때문에 중간 값은 안 되고, 여기서 보면 이거이거나 둘 중에 하나일 텐데, 아마도 둘 중에 하나가 도미넌트하게 스테이블하기 때문에 그 경우에 해당하는 것만 딱 보여준 거고, 앞에 11개점 있으면 이런 거를 바꿀 수 있는 찬스가 무지하게 많아서 복잡한 패턴이 생기지만, 이거는 딱 생길 수 있는 게 2가지밖에 없으니까 둘 중에 하나만 보여준 거라서 비교적 심플하게 나왔지 않느냐 하고 설명할 수 있는 거죠.
네. 이해했습니다. 감사합니다.
Any other question? 자, 질문이 더 없으면 아직까지 우리 많이 배우지 않았습니다. 많이 배우지 않았으니까 지금부터 필요한 것들 오게닉 1에서 조금 더 보충해야 될 것들은 가서 찾아보면서 공부하고, 2에서 지금 가는 거 이제 막 시작한 참이니까 지금부터 놓치지 않도록 계속 끝까지 잘 따라와 주기 바랍니다. 추석 잘 지내고 숙제 잘 하고 다음 주에 보도록 하겠습니다.
수고하셨습니다.
오케이, 바이바이.
감사합니다.